I'm going to talk about some, movement from GCM to regional applications, which is basically concerning to downscaling. And as I said, you look to be quite well trained already, so you probably know quite a lot about that. So just to summarize and to get some, say, common level of knowledge for that autumn school. Well, next, please. Well, so brief outline. We started. We will start actually with some overview of say transfer from GCM to regional information. I will show you some resolution example, which actually you already saw yesterday on Wednesday from Sylvia presentation. And some summary of downscaling techniques, statistical and dynamical, with the emphasis because that's something I'm doing to stress the dynamical downscaling and all the stuff below. Well, so just mention added value. Just to tell you, I have been in quite a good connection with ICTP and Filippo Giorgi, who is some kind of father of dynamical downscaling. That's something I have to mention, and I will talk about. I will show you an example of really very nice added value. There are actually already said something about Cordex. I will show you about some activities of Eurocordex as well. We will talk about briefly mention of validation and some, say, how to make the projections. And we will end up with some kind of mention of bias adjustment and weather generators as some kind of statistical downscaling and some conclusion. Well, so please. Well, so when talking about the connection between global modeling and regional information, that's again some figures you already saw, and you can clearly understand that there are actually some, say, global features, global patterns, and there are as well some, say, regional ones. And of course, for impact studies, that's actually the main issue of that. For impact studies and for vulnerability assessment, you definitely need local information, because mostly in applications you are interested in local issues. Click, please. Please click.
Yeah. Sorry. Okay.
So what GCMs provide us, so that's information on global to continental scale picture. That's they are quite reliable on this. It's already Sylvia shown you, and actually concerning regional scale, it's sometimes limited, and it depends strongly on the resolution of the GCMs. So please click. In global models, now we are talking more on, say, air system models, and that's again something which is much easier on a global scale to provide really full spread of information on climate system components. I mean, all the components of climate system, which is not so easy in regional models, or it's not so developed yet. Even though there are some attempts to couple atmospheric regional model with, say, sea model in some cases, some places where it's necessary. Well, next, please. And yeah, last but not least, in this, say, global effect, definitely you need for teleconnection effects, you need global model, global simulation, because you cannot see any teleconnection in limited regional model. Next, please. Well, basically, from what I said, you can see that GCMs have some problems which we would like to solve. That's one important one. It's actually scale of topography, and to get real height of topography, to get slope orientations and some specific orographic features, which really difficult to take or to have in GCMs, but you can clearly see that in high resolution of regional climate models. Next. Yeah, that's another point that GCMs, especially say that in previous times, that was pretty difficult sometimes to resolve exactly land use with respect to that resolution, and to resolve real coastlines, to resolve some gulfs and this kind of stuff. So that's another point. Next, please. And scale of land surface processes, again, that's something which in GCM within a grid box you can see really just not so really very precisely, but for as I said, for impact studies you need really local effects which can affect climate and even climate change signal, as we see later. So that's something which we need better resolved, even some land surface processes and all other issues. Well, that's about the resolution. So I took one nice example from Jens Christensen earlier presentation, and you can see how 300-kilometer resolution model or GCM can see Europe, which is what I was talking about. So it's topography and it's coastlines. This is in 50 kilometers and in 10 kilometers and going to 10 kilometers, it looks basically quite similar. That's the issue of domain size when actually looking at that quite big region. So 10 kilometers is really below the resolution, but definitely there are significant changes, especially in the topographic height, which can play a significant role in some cases. Next, please. Well, we have some problems with GCMs, as already we summarized some way. So they can reproduce climate features on large scales, but their accuracy is really decreasing when you move to from continental to regional and even local scales, just because of the lack of resolution. Please. That is really true for surface fields, which are really strongly dependent on that, say, small-scale phenomena and small-scale features. So that's typical connected with precipitation, surface air temperature, and extremes, especially extremes, which are critically affected by topography and land use. Please, next. Yeah. In many applications, actually, you need to assess climate change impacts, and you need information on surface climate change and regional to local scale. That's really becoming fundamental, as I said, for impact studies, for that vulnerability assessment, and just for decision making, because you have to, or quite a lot of decision making is done on, say, local scale. So that's really fundamental. Please, next. Well, concerning techniques, that's probably quite well known. So that you have two methods. You can use dynamical downscaling, which means, for those of you who are not so much familiar, which means something like standard weather prediction, which is done by nesting of a limited area, high resolution model in climate simulations. We are talking about regional climate model within GCM. So that's quite a standard procedure. There are some opinions if this is really fair and possible to do that. The practice is showing that really it works quite well. On the other hand, it's slightly different problem. In numeric weather prediction, it's initial condition problem when you are just talking about the differential equations and their solution. On the other hand, in this case, we are not so much interested in initial condition, but we are actually running that simulation just driven on the boundary. So it's that from mathematical point of view, there is some kind of disagreement of that, but actually, as I said, so it's practice is showing it works reasonably well. Another issue, another method for downscaling, which is actually pretty well known, is statistical downscaling. There are actually many methods for statistical downscaling. Basically, it's about identification of statistical relationships between large-scale fields and local climate variables, climate characteristics. Next, please. The former approach, which means the dynamical downscaling, seems to be more correct from a physical point of view because that's based on real, say, basic principles of physics and thermodynamics, and so it's conserving energy and all this stuff I am going to talk about just on the next slides. No, excuse me.
Oh, sorry, yeah.
So that we can hope that we will keep some physical consistency between all the outputs from the model. There is one point which we should have in mind, and that's concerning future simulations, because in the model there are actually plenty of parameterizations, and we just can only hope that these parameterizations, which are sometimes actually empirical ones, that we can hope that they will work in the future as well. Concerning statistical downscaling, that's something which you get some relations. You don't have so much consistency between the variables from statistical downscaling. On the other hand, as you can read, that the method of statistical downscaling are usually much less demanding concerning computer resources. So you can get actually much faster and much more information from the results. Well, next, please. So let's just one slide on statistical downscaling. So as I said, it's based on identification or finding some statistical relationship between large-scale fields and local surface climate elements, which is mostly done by or in terms of machine learning, some kind of data mining and finding predictors. Actually, basically on upper levels, and you are trying to get predictants on surface climate characteristics, extremes, and other variables, which actually needn't be even simulated by GCMs or even regional climate models. That's something I should say already here, but I will mention that later on as well, that actually you can use statistical downscaling both on outputs on GCMs, but you can use that as well on, say, not so high resolution regional climate models, which is maybe more convenient even because you have or you can hope that you will have, say, some kind of, say, better or more precise for the region of that inputs for your statistical downscaling. There are some methods here mentioned, regression analysis, which is some kind of very standard techniques, multiple linear regression methods used. You can use artificial intelligence techniques, neural networks, and there are some other pattern-based approaches, and as well we can include here stochastic vector generator, as I said, I mentioned at the end of my presentation. Well, next one. So the method of statistical downscaling is mostly used to resolve spatial variability that can be used as well for temporal resolution, and there is quite important assumption of stationarity to obtain the relationship, which actually that's one case to really establish the relationship. Even for that, you need some kind of stationary data, because if you don't have stationary data, if you have some, say, oscillations there, so you needn't get so strong relationship. And another important point is when I mentioned that parameterizations is in regional climate simulations needn't be exactly valid for future simulations. So that's extremely case or can be extremely case of statistical downscaling, because the relationship you get from present data needn't be valid in some, say, different climate state in the future. And just to conclude, that's an important point for, especially for statistical downscaling. It's definitely needs of data. You need actually plenty of high resolution observations data. You can use as well analysis, but mostly it's done based on observations, because the analysis sometimes are slightly biased as well as the models can be. So that's issue of data is really a very important one. And just if you need or if you like to get really high resolution statistical downscaling results or statistical downscaling outputs from say GCM or RCM, so you need actually the same resolution of observations for your variable you need to downscale. Well, next, please. Well, so now move to dynamical downscaling. So that's, I already explained that nesting of limited area to GCM. And I already even mentioned that equations which you have heard from Sylvia this week already on Wednesday. So not need so much to repeat that. Conservation of momentum, which is basically Newton's second law, describing the horizontal motion, conservation of mass, and conservation of energy. When talking about that horizontal or quasi-horizontal flow, I should say that you can use even full 3D equations, which is now actually getting to be more and more popular in when using just quasi-horizontal equations. Then it means that you use hydrostatic assumption on the atmosphere, which is not so much valid when going to very high resolution. It's not so much the case of GCMs, even though there are some experiments already with GCMs and showing quite, and that's something Sylvia mentioned as well, showing quite, say, challenging results in some cases. But in regional climate simulations, despite of, say, a few years ago, that was some kind of maximum resolution about 10 kilometers. So today there are experiments with some convection permitting simulations, which means non-hydrostatic simulations in about 3 to 2 kilometers. Well, next, please. Yeah, so in addition to that basic equations, there are actually many other processes which has to be parameterized. Basically, this scheme is really very similar to what you can see for GCMs, but definitely it's about the resolution. And in cases of some really high resolution, you can get some, say, processes described explicitly in the simulation, which is exactly the case I was talking about in the convection, which has to be parameterized in lower resolution simulation, but it's explicitly included in non-hydrostatic convection permitting simulations. So, yeah, next, please. Let's now ask the question, why regional climate modeling? So that's basically clear from what we already mentioned about, say, problems we have in GCMs, but definitely that when going to assess the regional climate, we have to keep in mind that it determined not only by, say, planetary and large-scale processes, but as well as the regional local-scale processes, and that's the main reason we are actually moving to regional climate modeling in the last step of that chain of tools. Please, next. Here's some example of North Atlantic oscillations. We have some kind of large-scale forcing, which you cannot get in regional models, but you need to downscale that because that's definitely driving the situation you have in the region. Next one, please. and that's can be transferred to the region. And what you need to see is the example of snowpack results for double CO2 for US, as you clearly see, and that definitely make a really difference. What you can see in regional simulations when you have a real or closer to real heights of topography in your model. Next, please. So in order to simulate climate, and especially climate change at the regional scale, it's really just necessary to simulate the processes on these all spatial and actually as well temporal scales, because in regional, in local applications, we can be really interested in even in things like, say, not only annual course, but as well daily course of some variables. If we have precipitation actually well in time when they happened, that's one example of difference between non-hydrostatic and hydrostatic simulations, for instance. So in non-hydrostatic simulation, we are getting better annual diurnal cycle of precipitation. Well, next, please. And there are as well some practical aspects of that, because in actually some about 10 or maybe even more years ago, when the regional climate modeling started, so then that time that was actually in a resolution about 50 kilometers, it was quite easy to run these simulations even on say personal computers. On the other hand, in say common move to higher and higher resolution, both in GCMs and RCMs. So today it's basically there is basically the same demands on run on simulations using regional climate simulations or regional climate models, because the resolution is really demand is to get really very high resolution from regional simulations. And from that point of view, when you are trying to keep some reasonably big domain to allow some development of regional features, so then it's becoming to be really very consuming as well. Well, next. Some comparison, maybe I can just only mention briefly. So we have some forcings in global scale and regional scale, which sometimes are actually even overlapping some way. And we have effects on general circulation. We have effects on regional climate. That's something we already some way mentioned. So maybe I can skip to discuss that so much. So please, next. That's example already I shown you, and you can see clearly here that say added value or benefit from using higher resolution regional simulation, because in global model you cannot resolve all the heights of topography where you can get snowpack and snowpack changes. And that's something which you can resolve in high resolution simulations, and you can get a proper answer on the questions actually when you have that precipitation fall, when you have discharge from the catchments, and when you need that water. So that's connection to impacts to hydrology. That's definitely need high resolution to get properly that issue or starting point with that snowpack generation and then melting. And well, this is for US, but we can see something similar even in alpine region. So that's valid more or less generally. Next, please.
Thomas, may I ask a question right now? This graph with the red and blue and green line, is that actually based on data, or is it just an image what could happen?
No, that should be data actually from that study.
Okay, thanks.
Yeah, that should be data. Well, that's another issue is aerosol forcing, for instance, which actually is showing even some other dimension or other direction of where regional climate model can go, which is some way similar to what GCMs when moving to air system model, actually including chemistry. So that's exactly what regional climate models are actually doing as well. So that aerosol issue and some chemistry, it's nowadays really getting to even to regional climate models. And the importance is that in addition to, say, some kind of global forcing through solar radiation, there is a regional, strong regional effects which is coming from really regional given sources of emissions of pollutants or aerosols, and for instance, SO2 here for China region. There are actually some studies on that, and this effect and this impact it's actually rather local. So that's a connection again of these global and regional issues. Next, please. Well, and last but not least, that's extreme events. That's something which maybe not so much necessary to talk about. That's just to show you that I don't have pointer here, but anyway, in the middle you can see Prague Castle, and actually view on that during that famous and really very strong flooding of 2002. Okay, next, please. And last but not least, that's something which actually we are doing in our department, so I had to include it, and we are actually preparing something for Cortex activity in this direction, and that's urbanization. That's in high resolution, in going to 10 kilometers, as you can see on the left panel, you can resolve the city, and we had that our meeting in Prague, so well, if you know Prague, so you can see that in a 10-kilometer grid, you can really get some part of the city in the grid box, so that to include properly urban effects, it's becoming to be quite important. And it really is, because on the right panel, you can see the resolution spread of temperature difference for night and day. And in red, it's during nighttime. And when you look to JJA column, which is summer, and nighttime, you can see that the difference, I mean the difference between city center and remote areas, you can get about 4 or 5 degrees of difference. So that's a really significant issue you should have in mind in going to high resolution of regional simulations. Well, next, please. Well, that's from one, say, starting Filippo's Georgi presentation, how that development of regional climate model began. So that's from some Yucca Mountain project. It was about waste, nuclear waste deposit, and there is actually first paper by Dickinson that Filippo was co-author as well, and they adopted just to simulate the conditions there for better assessment of hydrology in the region. That approach of simulations of limited area model driven by GCM, and then next, please. And then you made really full long-term or longer-term, 1 month long experiment driven by CNWF analysis and GCM fields, and that's kind of first generation of regional model or XCM based on MM4 that time model. So next, please. Concerning the development, that's definitely validation. It's an important issue that one starting experiment with every regional climate model is to run that within the reanalysis, as I already said. It's some kind of perfect boundary condition experiment, which enable you to really validate and to get validate your regional model and to get information on that property of your model. Today, there are more than 20 regional climate models available worldwide. As I said, they started in, say, about 100 or 50 kilometer resolution. It was in times when, say, resolution of GCMs was about, say, hundreds of kilometers, so that was still quite say benefit from regional simulations. Nowadays, it's some kind of 10 kilometers. It's standard, and as I said, so that there are many attempts nowadays to go to convection permitting versions. One important issue is that just to keep the regional model to simulate the effects of land surface processes. It's sometimes used spectral nudging, which means that larger scale effects you are forcing just not only on the boundary of the domain, but as well from the top of the model. And there are as well some attempts to use not only one way, but two-way nesting, which means to get back feedback to global model. But well, that's not so much done in the experiments. Next, please. Well, it's used for many process studies. That's maybe not so much necessary to describe so much here. It's a really huge spectrum of process studies to analyze the effects. That's something I am not going to elaborate so much. Please, next. I talk about coupling already some way about, let's say, in inclusion of sea or ice interactions, urban canopy and chemistry. So next, please. That's I'm not going to develop more. And of course, the main issue is to do real climate change studies, is that to get really regional signals. That's something I will address a bit in that say added value, and there are even some other use for follow climate studies and others. So please, next. And yeah, that's even used for seasonal prediction. And next, please. And yeah, impact studies, it's connected with climate change studies, so not so much need to talk about it. So next, please. Well, let's now moving to that added value. So let's you can find it. It's a paper of Filippo 2016 in Nature Geoscience, and it's about climate change signal in summer precipitation. And first, start with that left panel, so two columns. It's results from GCM and RCM. And you can see that some kind of scenario run for near future, far future. It's compared to, say, present control simulation. And you can see clearly the dots, which means that 3 from 4 models have this, say, direction of the signal. You can see, well, you could see that dots on the RCM column, but it's not so well seen, but it means 5 from 6 models with that direction of the signal. And what you can clearly see is that from GCMs, the simulation basically, it's alpine region if you haven't recognized. So in that region, you can clearly see that for GCM, you can get basically the decrease of precipitation, summer precipitation. Not say exactly uniform, but basically that's the direction. It's basically uniform, and that's decrease definitely. What you can see in RCM is that actually that is not exactly true. Actually, there is decrease in the vicinity of real alpine region, but on the alpine ridge, you can clearly see that there is increase of precipitation. And that is something which is really telling something and modifying really the signal you can get from GCM, which is definitely a really very nice example of added value you can get for say impact studies or whatsoever. And there is some analysis on the right-hand side. That's actually analysis of stratiform and convective precipitation. And you can clearly see that the signal is definitely coming from convective precipitation, from summer convection, which is something, again, a bit something actually telling us. So, please, next. And you can go even further and to analyze 95 percentile of the precipitation, so really extreme precipitation. And well, the structure is basically the same. And you can clearly see that mostly, even in the GCM, you can get basically decrease for all the region, even though it's not so high, and there are some, say, slight signal of say opposite direction for a very small part of the alpine region. But in regional climate simulations, you can clearly see that say the decrease of this percentile, it's in the vicinity of the alpine region, it's really pretty high. On the other hand, on the top of the mountains, that you get increase again. So that's added value. Next, please. Well, touching Cordex, which was already mentioned, so maybe we can go actually pretty fast. So there was some kind of phase one, which when Cortex started, and that the purpose was to provide really ensemble or set of regional climate scenarios covering that period discussed in climate change discussions, and to get that for majority of populated land regions on the globe. And important issue to make this data readily available and usable to the impact and adaptation communities. Next, please. There were actually generalized framework provided for testing and applying climate models basically worldwide in that regions. So next, please. And there were some effort made to foster coordination between regional downscaling efforts, just to involve, to make some kind of capacity building, and to involve local people from individual continents to start with that, which basically succeeded in many regions quite a lot. Well, next, please. That's phase one design, maybe, well, that's about that simulation starting from evaluation of the model using analysis and going to projections, and to make that something maybe we can skip, because that's probably you are familiar with that. So next, please. Just there are many regions actually covered, or basically all the continents. In some continents, especially the big one as Asia, there are actually more regions. We have in Europe as well one, say, pan-Europe region, and we have Mediterranean region. The focus of the phase one was on Africa to get some, say, information on the climate change signal there. Most of regions were run in 0.44 resolution. I mean in degree, it's about 550 kilometers resolution, and there are for Europe that was the round were made in 0.11 resolution, so in 12-kilometer resolution, and you can find this data actually on ESGF. Well, next, please. Well, this Cortex phase 2 already started just to better cover not only the regions, but as well some issues, some scientific questions concerning the scientific question that's actually flagship pilot study started. There are many of them already, and now there was some about 2 weeks ago. There were closure of another call where we applied just for that urbanization. So we will see. But anyway, so that's about that flagship pilot studies, and just to next, please. And to produce really coordinated sets covering reasonably well all the regions, because from phase 1 that was not exactly all were covered, so that's some kind of Cortex core experiment when this target resolution about 25 kilometers for each Cortex domain for a few scenarios and covered by a few GCM-driven experiments. And so it's really a very huge exercise, which actually cannot be done so much locally, but it's done rather by big centers around the world. Next, please. Well, that's still to foster communication and knowledge exchange between that regions and users and simulation. So next, please. And that's actually what you have already seen even today. So that's actually CMIP 6 plan, basically. And I should mention that in the development of that Cortex effort, that the principles are really getting closer and closer to the structure of standard CMIP protocols now with respect to the CMIP 6. And actually, you can see here on the really very right-hand side that's actually Cortex there included in S1 MIP in that. And it means, as I said, that the data are going to ESGF, and you can download the data from there. And we are in the simulations on Cortex. We are keeping the standards, as Eric mentioned, on the data outputs and this kind of stuff. So next, please. Concerning the FPS, there are some, say, a few target for applications, and horizontally you can see some, say, scientific questions or some, say, procedures development. And on the left-hand side, you have the list. I'm not going through the list because of time, but you will have the presentation there, so you can have a look if you are interested in some region. From Europe, we have basically 4 FPS now. That's convection FPS, that's land use FPS, and Mediterranean. There's anthropogenic aerosols effect, and there is actually air-sea interaction from Mediterranean. Well, next, please. Well, so that's concerning the validation. So as I said already, say perfect boundary condition experiments have to be validated to get information. You can validate that against original analysis just to get a real regional climate model bias. You can validate that against observations to show that, say, even or to avoid having the bias of the analysis. Next, please. And then you have to validate as well, say, control GCM-driven experiments or simulations, which is important because actually not exactly when having really some kind of perfect regional model based on validation, based on analysis driven, you can get in troubles in GCM simulations because even though you are carefully taking or carefully selecting GCM covering your domain of interest precisely, if there are some errors of that model at the place where you have boundary of your simulation, so you can get actually not correct boundary condition to your domain, and your regional simulation will get actually worse and worse, and that of course, well, not there is no reason to take actually worse GCM because again you can use that what's usually saying garbage in, garbage out. So you will have to take care about what's going in, but I'm saying that actually good results of GCM in your domain of interest needn't guarantee that you will get, say, perfect results with your RCM, even being as well more or less perfect on domain of interest. Next, please. Well, general remarks. In very high resolution, you can do basically direct comparison of your results to observation points. For low resolution, you should keep in mind that representativeness of the model outputs for the grid box, it's not exactly the same as the observation is. So that's some important point. And concerning the validation, you should as well go for full validation. I mean, not only in some kind of standard mean, but you should as well check the distribution, so other higher moments of the results. Well, and last but not least, that validation outputs can give you information which you can use for bias adjustment or correction, as you can see both terms in the literature or in the community, which are necessary to be used for scenario runs. Okay, so the scheme of that chain of progress when going from projections with GCM to the real, say, impact outputs. You can see that there are some kind of intermediate steps of statistical downscaling or regional climate simulations, or you can go even directly. All these steps can be actually or should be connected with the bias correction techniques. More or less, actually, many of the final stages are or can belong to bias correction methods, and there are some reason to do bias corrections in all these downscaling methods. One should say that when using statistical downscaling, you are you have quite tough connection between your GCM or upper levels from GCM runs and your observations, so that one could expect that even that relation could get you quite close to, say, real values. On the other hand, that's not exactly true for regional climate models, because regional climate models, as models themselves, have their own biases, which has to be reduced or adjusted. On the other hand, you can hope that you will get real regional processes there and their dependence on time for future scenarios. So that's quite an important issue. And actually having regional climate models as well as some kind of bias reduction tool. Well, Ensemble simulation, that's actually critical. It was already in that discussion at the beginning of today's session. And even for RCM, it's nice to have ensemble or big ensemble driven by, say, many combinations of GCMs that we are talking about some kind of matrix of the simulations. On the other hand, it's really a quite sparse matrix usually, because you definitely do not have all the combination between all available regional models and GCMs. On the other hand, there are some methods to fill these metrics, I mean statistical methods, but definitely it makes sense to use for impact studies not only one model, or if you have just only one model, so then that Janet talked about, it's necessary to compare your results and your line of outputs with, say, other available simulations, just to see some kind of, or to be able to assess the uncertainty, which is definitely a crucial point for impact assessments. Please. Well, and that importance of bias corrections, it's documented on that figure on the bottom. And that's definitely important when you have some process or some parameter which it's based on threshold. What I'm talking about, well, maybe this is some kind of yield based on temperature, but there is some kind of breaking point. And if you are around this breaking point, so bias correction in that case, it's really pretty important. Actually, maybe more clear example is when you are assessing, for instance, some kind of climate indices as number of summer days or tropical nights or whatsoever. So if you do not have bias corrected results, so you can get completely disaster concerning the number of these days and changes of these days. So that's definitely something you have to keep in mind, but probably you are aware of that. Next, please. So concerning the methods for bias adjustment or correction, actually there are some methods that, as I said, so regional climate model itself represents some kind of attempt, but standard statistical method, that's a delta method, which it's quite close to incremental scenarios, climate scenarios production, which was typical for, say, beginning of studies of climate change. You move just observations, analysis by climate signal from averaging GCM outputs. There is correction method, which actually is correcting individual model outputs based on, say, the differences. Both these methods actually can be developed a bit to get the different correction based on annual cycle or statistical distribution of the variable, and etc. And today, probably the most popular method, it's one-tile mapping technique, which is mapping real distribution of that variables to be studied. It's actually, while for temperature, the delta or correction method, it's basically pretty good. For some variables which have more stochasticity, so as for instance precipitation, or not so much Gaussian distribution, so it's actually quite important to do that this technique, and you can get really good results with that, as you can see on the figure. Please, next. There is one site I put here concerning that, so you can have a look. And next, please. Some warning concerning that bias adjustment. Even when saying that from regional climate model we have basically consistent variables, I mean the relation between them. So when using bias correction, you can lose actually that consistency. Well, next. And that's basically last slide of some, say, information. The weather generator, which is quite popular technique sometimes, while that bias correction method are actually pretty easy to use for some kind of climate characteristics, like say monthly or long-term averages. Well, despite it, there is some techniques to use that even for daily data, but it's actually here for weather generator, it's actually typical tool just to be used based on climate characteristics. I mean distributions and all the moments, and even some kind of autocorrelation between the data. So it's definitely some kind of statistical generator of time series, real-time series, which correspond to, say, climate characteristics coming from GCMs or even lower resolution RCM. So that's something which can generate time series for impact studies, and that's actually much faster, and that can generate quite long time series and to study that quite well. So that's I said, and nowadays actually even some attempts to, next please, some attempts to get even spatial correlation to that, just to be able to cover not only one single point, but to cover even some area. Next please. And just concluding, it seems to me I was actually quite longer than planned. Downscaling, it's a really important tool to get localized products for vulnerability and impact assessment. So that is something which you need for some, say, decision making, for measures of adaptation on climate change. So that's actually really important to get local information via downscaling. We can compare dynamical versus statistical downscaling, or we can use both of them as I showed. So that's not exactly just in opposite sides. So it can actually be quite good cooperation in between both these methods, which definitely has to result in bias correction to establish really full chain for application, for real application in impact studies. And one point which I should stress as well, it's that you should keep in mind that added value, which should be in your chain of tools, just to maintain it, not to by some, say, statistical approach or even concept, just to forget that added value, which could be in that, say, regional simulations or in elaboration of or when you are working on that on your problem on some impact study.